In the last few presentations, we completed the implementation of half adder and full adder by using the NAND and NOR gate only. Now in this one, we are going to implement the half subtractor by using the NAND gate only. So this is sometime an important question in the exam. They will ask you to implement the half subtractor or full subtractor or adder by using the NAND gate only or by using the NOR gate only. And if you have not practiced it earlier, then definitely there is a chance that you may be stuck at that point. So let's move to it directly. You already know what a half subtractor is. You know how this table has been written, you know how this expression has been written, and the implementation of the circuit. But for the one who don't know, and also for the revision purpose, let me brush it up in 30 seconds and then we will move to the NAND gate implementation part. So here A, B are the two numbers. Both of them are the single bit number. Because it is a half subtractor, it will subtract only a single bit number, and I want to subtract B from A. Okay, and there are four possibilities, okay, because there are two variables. So 0 is A and 0 is B in the first case, and if I subtract 0 from 0, definitely the difference D is 0 and also the output borrow will be 0. Similarly, if I subtract 1 from 0, I have to take the borrow, so the borrow output will be 1, and once I took the borrow, the 0 will become 2, and 2 minus 1, the difference will be 1. If you are having problem understanding this, how it will be 2 by taking the borrow, go to the playlist and search one of my lectures in which I explain the binary difference or subtraction of the binary numbers. It will be clear to you. Then 0 subtracted to the 1, I am having the difference 1 and there is no borrow required, so borrow is 0, and 1 minus 1, very simple, difference is 0 as well as the borrow is 0. And you can see that the difference is what? Odd ones detector. Whenever there is odd one on the left hand side, the D is high, which means that it is a XOR operation. So D is equal to A XOR B, and B output is very simple. It is high only for one case, when A is low and B is high. So A complement B, and I have implemented it just by using a XOR gate, a AND gate, and a NOT gate for A complement. Now let's move to the NAND gate implementation part. I have to implement this thing. Okay, so I will first go for the difference, and for difference you can clearly see that I require a XOR gate, and I will try to make a XOR gate by using the minimum possible NAND gates. So let's do it. Let's make a XOR gate by using a NAND gate. You are going to require 4 NAND gate for implementing a single XOR gate. Now the first number is your A and the second number is your B. I will give A as one of the input to this NAND gate, and I will also give B as the second input to this 2 input NAND gate. Now the output of this gate will act as the second input for these 2 NAND gates, this one and this one, and the output of these 2 NAND gates will act as 2 of the inputs for this 2 input NAND gate, the last NAND gate here. And the output of this gate will definitely be our difference, which is A XOR B. Okay, it's very simple. It is very easy to prove it. You just follow the gates, and at this point find the function, at this point find the function, and finally at this point try to find out the function. You will see that it is equal to A XOR B. I have done it in 2 lectures, so if you are following my lectures, then definitely you know how to do these things. It is something that I'm not going to explain you right now. You just know that, yeah, this particular configuration gives you XOR as its output. Now the only thing left is A complement B. So we are not going to make the bunch of NAND gate to implement first the A complement and then to implement the AND operation. It is actually the not optimization of the gates. Okay, you are going to use lots of gate which is not your actual answer. You will lose your marks in that. So what we will do, we will try to find out some point in this configuration from where our task is going to be easier. So let's see how to do it. At this point, if I ask you what is the value, what is the output, then let's see what it is. This is A coming here, this is A coming here, this is B. So at this point we are having A and B, and then its complement because it is a NAND gate. So A, B and whole complement is one of the input to this gate, and B is the another input. So let's see what we are having at this point. A, B whole complement and B, and then its whole complement. Fine. And when you open it down, you will find it like you're having A. I'm just trying to open this thing, this complement thing, then it will be A complement or B complement, and there is B, this B, and then the whole complement of this thing. Now I'll try to open this bracket by distributive law. So I'm having A complement B or B complement B and then whole complement. You very well know that B complement B ANDed operation of B and B complement gives you 0. So you are left with A complement B and its complement. So only thing I need to do is to complement it again. If I complement it again, what I'm having A complement B. That's our borrow output. So let's do it. Let's do this. I just want to give it again to a NOT gate, and you know how to make a NOT gate by using the NAND gate. You just keep the input same, both the input same, it will act as the NOT gate. So we are having the borrow output as A complement B, its whole complement, and again we are using a NOT gate, so then complement, and this complement will be cancelled out, and we are having borrow output as A complement B. So this is how we have to implement the half subtractor by using the NAND gate only. So see you in the next